All right, so let's look at the last state of matter for our discussion from Chapter 9. That's going to be gases. So the question is, how do gases behave under pressure? Well, there is one big equation that we use to define gases, and that is the ideal gas law. And you guys will need to be familiar with this equation, but we're not going to use this directly. You'll see momentarily that we're going to focus on a couple of special cases. But in general, this is true for all gases, that the pressure times the volume is equal to N times R times the temperature. That's a number of atoms or molecules. That's called a constant. I think it's the Rydberg constant. But anyway, that will be fixed. We're not going to add atoms or molecules or take them away in the middle of a problem. And that R is a constant. What we will change is the pressure, the volume, or the temperature. And I note here that temperature needs to be in Kelvin. We are now at the point where you must convert temperatures into Kelvin. If they are given to you in Fahrenheit or Celsius, and you try to use this equation, it's going to give you bogus results. That temperature has to be in Kelvin. All right, well, let's look at some special cases. So first off, let's consider applying a constant pressure. If we were to apply a constant pressure, then this P would be fixed. It's just some number. We already said N and R were some number. So really we get the relationship that V equals some number, some constant times T. And we could rearrange that further, dividing by T, to get that V over T is a constant. The volume divided by the temperature is always the same. Well, if the volume divided by the temperature is always the same, then we get what is called Charles's law. Volume over temperature initial equals volume over temperature final. Or I'll often use 1s and 2s, or possibly even 3s or 4s if we have several different situations we're moving through. But throughout any process, if we're leaving the pressure constant, this is always true. The volume over the temperature must be the same. So if there's some value at the beginning, that same volume divided by temperature at the end better be the same. Your equation sheet has this written slightly differently as V naught over V final equals T naught over T final. I prefer to use this one. I would encourage you guys to write this one down on your equation sheet when going through this chapter. I like to do it this way because it puts the initial and the final in the same place. The equation sheet as is has all of these same variables stacked with each other. You know, there's some merit to that. There's arguments you could make as to why to use it this way. But personally, I like to group it so that it's before and after, all together, so we can group up our variables at different points in time or in different places and keep them in nice, tidy groups. That just makes more organizational sense to me. And remember, these temperatures better be in Kelvin. We have temperature ratios here, which is what I warned you guys about. If we had some initial temperature like 20 degrees Celsius and some final temperature like negative 100, which we're going to see in an example, we would end up with a negative ratio, which would imply that we should have negative volume. And negative volume doesn't exist. I make the same offer every year. If you guys can go to Walmart and find me a water bottle that holds negative 1 liter, I'll give you $100, but you're not going to find it. And with the way things are right now, I'm not going to encourage you to go out to stores and spend hours looking for something that's not there. So please don't actually go look for negative volume. Just trust me, negative volume does not exist. That is why we can't have negative temperatures. And we must keep our temperature units in Kelvin. But ultimately, Charles' law says something pretty basic. If the temperature goes up, the volume goes up. If you heat a gas, it expands. If the temperature goes down, the volume goes down. If you cool a gas, it contracts. They are what we call directly proportional. When one goes up, the other goes up. If one goes down, the other goes down. That's what this says in words. We can use this equation to come up with the exact numbers to go along with it. But you should know what to expect in problems. If the temperature goes up, you should expect the volume to go up, or vice versa. Now let's look at another special case. What if we held the temperature constant? Well, if we looked at the temperature being constant up here, we would have nR, which is a constant, times temperature, another constant. This would all just multiply to be one big constant, telling us that P times V, pressure times volume, should remain constant. It should always be the same. And that gives us Boyle's law, that if we multiply pressure and volume at any point in time, initially it equals something, that something stays constant, so finally it equals the same thing. PV initial equals PV final, or P1V1 equals P2V2 equals got a tongue twister there, P3V3, and so on. And again, I like to write it this way so that I can put my initial pressure and volume together, my final pressure and volume together. But your equation sheet has it grouped with the actual variables that are the same together. V final over V initial equals P initial over P final. I like this one even less. Again, I will encourage you guys to write this on your equation sheets and use this equation, this version of the equation, when trying to work problems from this chapter. But again, this actually doesn't say anything too complex. It's fairly intuitive. If you increase the pressure, if the pressure goes up, the volume goes down. You squeeze on some gas, you can shrink its size. If the pressure goes down, volume goes up. You stop squeezing, it expands. These are fairly straightforward concepts, fairly straightforward equations, and most people have a decent time with this material. It really isn't too bad to recognize when to use your respective equations, and actually the algebra as well is fairly straightforward when using these. So one last page and we will be finished for this chapter. Thinking about Boyle's law and Charles' law, it actually is pretty tricky to determine volume. Both of those things change the volume. So combining these effects makes it tricky to determine volume. And therefore, volume needs to be defined at a standard temperature and pressure, or what's called STP. And those things have been decided to be 1 atmosphere of pressure. I mean, that's what we're sitting under most of the time. 1 atmosphere is above us. And the temperature was chosen to be 0 degrees Celsius, the freezing point of water, which would be 273 degrees, not degrees, just Kelvin. 273 Kelvin is standard temperature. But it doesn't just stop there. Measuring gas pressure can be tricky too, because inside a container of compressed gas, there is pressure, but outside of the container, there may also be pressure. For instance, there's 1 atmosphere of pressure on Earth's surface. We often refer to gauge pressure as the difference in pressure, the inside pressure minus the outside pressure, because that is what a gauge would read. So, for example, if you have some container with compressed air at an absolute pressure, that is what the pressure actually is, the absolute pressure of 5 atmospheres inside this container, it would have a gauge pressure of 4 atmospheres on Earth, because that's 5 atmospheres inside the container minus 1 atmosphere outside of it. But if you take this same container to space, it would have a gauge pressure of 5 atmospheres. There is no atmosphere in space, and there is no external pressure. So 5 atmospheres inside minus 0 outside gives us a gauge pressure of 5 atmospheres in space. That's just a subtle distinction that I wanted to make clear to you all. Please, as usual, if you have any questions, let me know. I'm always available via email, and I've started doing video tutoring sessions. Just schedule a block of time with me through my Calendly, calendly.com/Ryan-Lapham. I've posted the link several places. But that actually concludes our notes for Chapter 9. I will follow this up with a series of videos working various examples using all of the equations we've covered.